Today, it is our pleasure to have Zhongshan from University of Connecticut, and she will talk about the static vacuum extensions of Bartnik data near flat domains. Please, Zhongshan, you can start, and welcome.
Thank you very much. Thank you everyone for coming and providing me this opportunity to talk about our work on static vacuum extensions for Bartnik boundary data. This is a joint work with Lan-Hsuan at UConn. I think she's also here at the meeting today, and I'd like to thank her for working together with me on this topic. So let me first introduce to you the static vacuum pairs and Bartnik data. So here we consider a smooth manifold denoted as M. It's an n-dimensional manifold and a pair GU consisting of a remaining metric G and the function U on this manifold is called the static vacuum pair if this following system is true. So like the first equation is saying that U times Ricci tensor of G is equal to Hessian of U, and second equation is saying that U is a harmonic function with respect to G. It's also equivalent to say that the metric G is scalar flat. Static vacuum pairs are very interesting and important in general relativity. One aspect is that if we have a static vacuum pair GU on the remaining manifold M, then we can construct this space-time, it's like M cross R, and equip it with this product metric. And this space-time will be a static vacuum space-time. It's static in the sense that the space-time metric is invariant under time translation, and there is no shift vector everywhere. And it's vacuum in the sense that this space-time metric satisfies the vacuum Einstein equations. Okay, and well-known examples are those two space-time, Minkowski space-time and the Schwarzschild space-time. So here in Minkowski space-time, the remaining metric we consider is the flat metric on Rn, and the function U is the constant function 1. We also call this function U as the potential function for the remaining metric. And then in the Schwarzschild case, the remaining metric is this part, which is also called the Riemannian Schwarzschild metric. And its potential function is just square root of this coefficient. Okay, so that's the examples for static vacuum pairs. Static vacuum pairs are also important in the study of scalar curvature deformation. Like we know that if a remaining manifold does not admit non-trivial solution to this equation, then the scalar curvature map will be linearization stable at the metric G. Which means that if we have a, say, scalar flat deformation at G, then we can always deform this metric along that deformation in a family of metrics with fixed scalar curvature function. Okay, that's the meaning for linearization stable. And the reason for this is that if we consider the scalar curvature map, which maps the metric G to its scalar curvature, then if we compute the O2 formal adjoint of the linearized operator at a background metric G, it will be in this format. Okay, that's called the like formal adjoint of scalar curvature operator. Okay? And we observe that like if this background metric G has flat scalar curvature, then this equation is equivalent to the static vacuum system. Okay, so that's the aspect of static vacuum in the study of differential geometry. Okay, so since static vacuum pairs are very important and interesting, we would like to know the existence of such pairs. Okay, and here are some results we have. In the complete case, we know that a complete 4-dimensional static vacuum spacetime, actually we can say more generally, a stationary vacuum spacetime must be flat. This is first proved by Lichnarowicz with the assumption that the spacetime is asymptotically flat, and then it's proved by Anderson with no asymptotic assumption. Okay, And in the non-complete case, we have this very well-known uniqueness of static black hole theorem, which tells us that Riemannian Schwarzschild metrics are the only asymptotically flat static metrics whose boundary is a minimal surface. Okay. And we also have, besides those, we also have a large class of axisymmetric solutions, which are called the wild metrics. And those metrics have various boundary geometry and different asymptotic behavior. Okay, so in this talk, we are interested in finding asymptotically flat static vacuum pairs. And we see like if the manifold is complete, then asymptotically flat pairs will just be the flat pair, the Euclidean metric with constant 1, the potential function should be constant 1. And if the manifold is non-complete with non-empty boundary, then we need to impose boundary conditions. But if the boundary condition is too strong, such as what we have here, if the boundary is a minimal surface, then we will only have Schwarzschild solutions. Okay, so in order to come up with like static vacuum pairs other than this Schwarzschild family, we want to impose appropriate geometric boundary conditions to the static vacuum system. And here we will consider the Bartnik boundary condition. Okay, so let me, before I introduce the Bartnik data to you, is there any question? If you get any question in the following talk, please feel free to interrupt and ask me. So Bartnik boundary data arises in the study of mass in general relativity. In GR, we have a very well-defined notion of total mass for asymptotically flat initial data sets. So if M and Mg is an asymptotically flat Riemannian manifold, then we can define the total mass, also called the ADM mass, in this formula here. It's just a flux integral at the asymptotic infinity. Okay, and ADM mass is very well studied. We have the like famous positive mass theorem, which says that like if M is complete, asymptotically flat and connected, if G has positive non-negative scalar curvature, then ADM mass will be non-negative. Okay, so that's the very good notion of total mass, but different from total mass of asymptotically flat manifold. For compact manifold, we don't have a unique notion of like local mass. There are various interesting and important notions of quasi-local mass for compact manifold, and Bartnik quasi-local mass is one of them. Okay, so here we consider omega and G naught as a compact manifold, and it has non-empty boundary sigma. Scalar curvature is non-negative. That's the we also impose like dominant energy condition on this G naught metric. Then we can define the Bartnik mass of this compact manifold as here. Bartnik mass of omega G naught is to take the infimum of the ADM mass of all the possible extensions of omega G naught. Okay, so here this extension Mg should be such that firstly, Mg should be asymptotically flat. Okay. Secondly, it satisfies this dominant energy condition. And then lastly, the boundary of the extension M can be identified with the boundary of omega. So like in this picture, we can glue those two regions together to get a complete asymptotically flat manifold. Okay. And then along the boundary, we should have those two conditions hold, which are called the Bartnik boundary conditions. Okay, the first condition is saying that the induced metric on this boundary manifold from the exterior metric G should equal to the induced one by the interior metric G naught. And the second condition is saying that the mean curvature of the boundary manifold of sigma at the boundary of the exterior region should equal to the mean curvature of sigma as the boundary of the interior region. Okay, so you see that the mean curvature should be continuous across the boundary. Okay, so we consider all those possible extensions and compute the ADM mass of them, take infimum, that's the definition for the Bartnik quasi-local mass. Okay. So here, this is a picture for the definition of Bartnik quasi-local mass, and let's take a look at the Bartnik boundary condition. The first condition is very natural because we want to glue the two boundary manifolds together. We want to identify those two boundary manifolds. Of course, we would like the induced metric to be the same. And then the second condition, equation equality on the mean curvature. This is necessary for the scalar curvature of this glued manifold to be well-defined distribution only. Okay, so here is the Gauss equation across the boundary. We see that the scalar curvature of the ambient metric can be written in terms of like intrinsic and extrinsic curvatures on the boundary manifold. And let's take a look at the leading order terms. This is scalar curvature of the boundary metric, and this is well defined because we have the first equality here. And this leading order term is normal derivative of the mean curvature. So for this term to be distributionally well defined, we should have this mean curvature to be at least C0 across the boundary. Okay, so that's the reason we have the second equation in the Bartnik boundary condition. Okay. So here we have two conjectures for the Bartnik quasi-local mass. The first conjecture says that if the Bartnik mass of some compact manifold is realized by an extension mg, then this mg must be static vacuum in the sense that there exists a potential function u, so that g paired with u is an asymptotically flat static vacuum pair. Okay, here we see g is asymptotically flat if g decays to the flat metric, and u should decay to the constant function 1 at infinity. Okay, so the first conjecture is proved to be true by Anderson and Haurigi in a paper in 2019. Okay, so we know like the minimizer must be static vacuum. Therefore, we want to ask, can we always find a static vacuum extension which realizes the Bartnik mass? So this gives us the second conjecture, which says for this omega g naught, we can find a unique asymptotically flat extension so that it is static vacuum. So we have those static vacuum equations hold on the manifold M, and it satisfies the Bartnik boundary condition on sigma. Okay, so this gives rise to the boundary value problem we want to talk about today. Okay, so questions so far? Okay, and the remark about this here, we want to suppose that the mean curvature Hg naught is not everywhere less than or equal to 0 on the boundary, because we want to make sure that if we get an extension for this omega g naught, then we don't want a minimal surface in the exterior region. Okay, because we know static vacuum extension with minimal surface must be Schwarzschild. Okay, so that's our, so here we have the boundary value problem, and we want to study the existence of solutions to this boundary value problem. Okay, so we have prescribed data tau and phi on the boundary manifold sigma. You can think of tau as a Riemannian metric, and phi is a scalar field on sigma. And then we want to find this pair GU, G decays to the flat metric, U decays to the constant function 1. So that it is static vacuum, it satisfies the prescribed Bartnik boundary condition. Okay, so this is a very interesting and natural geometric boundary value problem. However, not too much is known for the existence of this problem. Okay, here is a list of results from previous work. So in dimension 3, there is this local existence and uniqueness for Bartnik data, this tau phi, this pair, which are close to the Bartnik data of standard two-sphere in R3. Okay, so here is the induced metric on the standard sphere. Here's the mean curvature. So if tau phi is close to this data, then we know we can always find a static vacuum extension which solves this boundary value problem. Okay, so this local result is first proved by Pengzi Miao under a symmetric assumption, and then it's proved by Anderson in the general case. Okay. And in another work by Sederbaum, Renyi, and Strello, the authors provide a flow approach to solve this static vacuum system for axis-symmetric boundary data, also in dimension 3. Okay. And besides that, we have existence of stationary vacuum solutions subject to different choices of boundary conditions. Okay. Like stationary is a more general case for static. Okay, and in the following, I will show you what we have done for the local existence and uniqueness result when we consider boundary data that are close to flat data. Okay, so that's the introduction part. Any question? Okay. So in order to introduce to you the main results in our paper, I would like to first discuss this concept called static regular. Okay, so here is the definition for static regular. Now here in the following, we will always consider this manifold M as the exterior region in Rn. M is equal to Rn minus some open bounded domain omega. Okay, and sigma is the boundary of M. We call this boundary sigma as static regular in M if any static vacuum deformation preserving the Bartnik data also preserves the second fundamental form on the boundary. Okay, that's the definition for static regular boundaries. Okay, I will explain this in more detail to you later. Let's first take a look at the result we have. With this definition, we show that if the boundary is static regular, then we have local existence and uniqueness for the boundary value problem. In more detail, we show that if we have a, we show that if we have a data tau and phi, which is very close to the Bartnik data G sigma H sigma, which is the Bartnik data on sigma induced from the flat metric in the exterior region, then we can always find a asymptotically flat static vacuum pair GU, which is close to the flat pair, and this metric G realizes the given Bartnik data on the boundary manifold sigma. Okay, that's the local existence part, and moreover, we show that this solution is unique, it's geometrically unique in the sense that if we impose a gauge condition, then this GU must be a unique pair. Okay, so that's the local existence uniqueness result for static regular boundary. Okay, so let me show you the idea of this static regular concept. Here we want to consider the boundary value problem as a map, and then we try to apply this implicit function theorem. Okay, so you see now M is exterior region in Rn, and we construct this map L, which maps a pair GU to the static vacuum equations on M and the Bartnik data on sigma. Okay, so you see if the first two components are 0, then GU is static vacuum. And we want to prescribe the last two components. Okay, and then we take linearization of this map, linearize the map at the flat pair. Okay, so we get a linearized operator acting on the deformations HV. H is deformation of metric G, V is deformation of the potential function U. Okay, we get this linear operator. And we want to apply implicit function theorem, which tells us that if we can show the linearization of the map is, let's say, isomorphism, then we can say, oh, it's locally isomorphism. We can always find a solution for given data. Okay. However, this is not true. With a simple observation is here. Like static vacuum property is invariant under diffeomorphisms, which means that if GU is a static vacuum pair, so if L of GU is equal to 0, 0 in the first two components and equal to tau and phi for some boundary data, then we can always consider an arbitrary diffeomorphism of M to itself, so that the diffeomorphism is identity on the boundary, and take pullback of the pair via this diffeomorphism. Then this map acting on the pullback pair gives the same image as before. So this pullback matrix is also static vacuum and it's with the same Bartnik data as before. Okay, so this tells us that in the linearization sense, for the linear operator, we have a large class of kernel elements. All those kernel elements look like this. H is the derivative of the flat metric with respect to some vector field X. X is vanishing on the boundary and V equals to 0. Okay, like for arbitrary X, this is always a kernel a kernel element for the linearized operator. Okay, so this is good, but it's just not good, but good in another sense that those kernel elements are kind of trivial because they are generated by different choice of gauge, or they are generated by diffeomorphisms. Okay, so in order to mod out this big subspace of the kernel space, we can just impose gauge condition. Okay, so here it is proved by Anderson and Curran that under the harmonic gauge, this linear operator is elliptic in the sense that the kernel space has finite dimension, also has finite dimension co-kernel, and they show that the index is actually 0. Okay, so therefore, to prove local isomorphism for this nonlinear map, we want to show that moduli gauge, or moduli those kernel elements generated by diffeomorphisms, this linear operator should have 0 kernel, should be an isomorphism. Okay, this is equivalent to the statement here. We want to show that any kernel element of the linearized operator must be a diffeomorphism deformation. More detail, if we have HV solves this equation, it solves the linearized static vacuum equation. It preserves the Bartnik data, like those linearization of Bartnik data with respect to H on the boundary should be equal to 0. So if HV is a kernel element of the system, then we want to show they must be trivial in the sense that they must be generated by gauge, by diffeomorphism. Okay, here we call, like if HV satisfies the first two interior equations, we will call HV as a static vacuum deformation. And if H satisfies those boundary conditions, we say H is preserving the Bartnik data. Okay, so I want to show any static vacuum deformations preserving the Bartnik data must be diffeomorphism deformations. Okay, so that's the idea of this boundary value map. And actually, this is kind of a hard question. Oh, yeah, sorry, I pressed it. Sorry, I pressed the wrong button. Okay, so we come to here, want to solve this question, but it's hard. Okay, because the boundary data, we only have the Bartnik boundary data for it. Okay, and our first observation is that actually Bartnik data is important not only for the definition of Bartnik quasi-local mass. Bartnik data also arise from a variational problem. So here we consider this functional called curly f is integral of u times f is acting on a pair GU. So it's integral of u times scalar curvature of G and minus a mass term. Okay, this functional comes from the Relativity Hamiltonian. Okay, and then we take variation formula for this f. The first variation formula is given here. And you see here, it's just the adjoint operator of linearized scalar curvature map. Okay, so if GU is static vacuum, this will be 0. So static vacuum pair will be critical points for the functional f, in the sense that this will vanish and the boundary term will also vanish if the deformation H is preserving the Bartnik data. Okay, so that's the first variation. We see Bartnik data arises here. And we take second variation of the functional at a static vacuum pair, we'll get this formula. Here, this P is just linearization of those static vacuum equations. Q is linearization of those pairs, those boundary terms. Okay, and we know that second variation is symmetric with respect to K, like the two deformations HV and KW. Okay, so based on symmetry of second order variation, we can derive this identity for any two pairs deformations HV and KW, like those, like this is equal to that. Okay, we call this as green type identity because this is very similar to the green identity we have for a Laplace operator. If we write it here. So for Laplace equation, we have, say, integral m Laplace u times w plus integral along the boundary, normal derivative of w u. This should equal to Laplace w u. Okay, so this is like here we are considering Laplace operator with dirichlet data. Here we are considering static vacuum operator with Bartnik data. Okay, so that's the identity we have. And in particular, if we know that HV is a static vacuum deformation, preserves the Bartnik data, then we can plug this HV into the identity here. We see this will vanish, and we choose KW to be an arbitrary static vacuum deformation. So this term will also vanish. We are left with this term, and it reads this boundary condition of HV paired with the Bartnik boundary data of K should equal to 0. Okay, this is kind of telling us that this term, the Bartnik, this new boundary data of HV is kind of like the L2 formal adjoint of the Bartnik boundary map. Okay, so like if we have a kernel element and that kernel element has non-vanishing geometric data here, that will be the co-kernel element. Okay, so we see, let's again take a look at the linear order term in this boundary data. That's A prime H. It's the linearization of the second fundamental form on the boundary with respect to H. Okay, so we ask, what if this term is equal to 0? Okay, so therefore, instead of considering Bartnik data, we want to consider Cauchy data first. Okay, so we enhance the kernel space to be static vacuum deformations where H is preserving the induced metric and preserving the second fundamental form. Okay, we call this as the Cauchy data. Okay, so we show that if H is static vacuum with 0 Cauchy data listed here, then HV must be trivial in the sense that HV must be deformation generated by diffeomorphisms. Okay, so here is a rough sketch of the proof. So from the boundary data here, we know induced part of H on the boundary is equal to 0. Actually, we want to get the full tensor equal to 0 on the boundary. And this is easy to manage. We can just transit H by a kernel element, or we can choose a different gauge for H. Okay, same thing for A prime H. A prime H essentially tells us that normal derivative of the induced tensor plus some extra terms should equal to 0, and we can always choose the correct gauge so that this is vanishing on the boundary. Okay, so the first step is starting from this Cauchy boundary condition, we choose a gauge. So we add to H a trivial element, the derivative of G with respect to some properly chosen vector field Z, so that this new tensor H tilde has vanishing Dirichlet data and vanishing Neumann data on the boundary. Okay, and since this H tilde differs from H only by a kernel element, by a trivial element, this H tilde satisfies the same equation as H. Okay, so we take the first equation here, replace H by H tilde, and consider this equation on the boundary. We contract the equation, let me make it larger. We contract the equation on both sides with the unit normal n. Okay, we get Hessian V contracted with n should equal to Ricci prime, linearized Ricci tensor contracted with n. Okay, and on the right hand side, this term is actually equal to 0. Because we can consider the Gauss-Cauchy equation, we know that Ricci tensor contracted with unit normal vector can be written in terms of those extrinsic and intrinsic curvatures of the boundary manifold. This is true for all metric, so we can take linearization of those equations. We take linearization, of course, with respect to H tilde. And since H tilde has vanishing Cauchy data, like vanishing Dirichlet and Neumann data, when we take linearization, all those terms will be 0. And H tilde is also a scalar flat deformation, so this term is also 0. So we can derive that the term on the right-hand side is equal to 0. Therefore, Hessian of V contracted with n is equal to 0 on the boundary. So we get this system for V. It's harmonic inside. We have this boundary condition, and it decays to 0 at infinity. From this, it's very easy to derive that V should be 0 everywhere. Okay, excuse me. Okay, questions so far? Okay, so once we have V equals to 0, we can plug those back to here. We see now H tilde must be a Ricci flat deformation. It's Ricci flat deformation in the exterior region. It has vanishing Cauchy data on the boundary. Okay, so from here we can derive actually H tilde is trivial. It's generated by diffeomorphism. Here is a picture for the proof. We consider the exterior region have this H tilde. We know H tilde vanished to the first order on the boundary. Therefore, we can extend H tilde by 0 inside. So we get the globally defined two tensor H tilde on Rn, which is C1 smooth. And we can prove actually it is a weak solution to the Ricci flat equation. Okay, so here, if we pair H tilde with any linearization of Ricci tensor, this K is arbitrary two tensor deformation K. Take integral, this integral should be integral in the exterior region, integral of the interior region. This term is 0 because H is 0 in the interior region. For this term, we can take integration by parts or use the green type identity I showed you before. So we can remove this Ricci prime operator from K to H tilde, and we know this is 0 in the exterior region. And from integration by parts, we will have boundary terms, but the boundary term involves at most first order derivative on H. And we know H managed to the first order on the boundary. So this term is also 0. Okay, so H tilde is now globally defined. C1 smooth tensor is weakly solution to the Ricci flat equation on Rn. And from here, we can easily derive that H tilde is must be generated by a diffeomorphism. Okay, so once H tilde is diffeomorphism deformation, then we come back to H. That will also be a diffeomorphism deformation. Okay, so you see, like Cauchy data is a very good choice to prove this diffeomorphism deformation for H and V. And this is the crucial observation for us to define this concept of static regular. Okay, it's static regular if any static vacuum deformation with 0 Bartnik data must also have 0 Cauchy data. Okay, that's the crucial reason for this deformation. And based on the observation here, we do extra analysis on this co-kernel and kernel space for the map out here. We also take very careful calculations with the asymptotic behavior of all those tensor fields. And then we get this find local existence and uniqueness result for static regular surfaces. Okay, so questions so far? Okay, so now you may ask me what surfaces in Rn can be static regular. So let me introduce to you the second part of our results. We show that those surfaces are regular. Firstly, if omega is a bounded open subset in R3, so that its boundary manifold has positive Gauss curvature, then this boundary sigma must be a static regular surface. Must be a static regular boundary in the manifold which is exterior to it. Okay, that's the first result. And second result says that actually in Rn, static regular surfaces are open and dense. Okay, in more detail, if we consider, here's the picture, if we consider a family of omega t, which are bounded open subset, their boundary are a family of surfaces sigma t. They are embedded hypersurfaces in Rn. Here's the picture, and the deformation vector is a rescaling of the uninormal vector, and the scalar c is positive almost everywhere. In this case, we can find an open and dense set J, so that any sigma t lies in this interval must be static regular. Okay, and this good interval is open and dense, which means like in this picture, so have family of surfaces, then good surface, static regular surfaces are the red ones, and bad, like singular surfaces might only be discrete point in this interval. Okay, and from another aspect, we can see that if we have a surface in Rn, and if it happens that this is a bad surface, it's not static regular, then we can actually always perturb this surface along the uninormal vector, uninormal direction, perturb it a little bit, that will become a good surface. Okay, so that's the that's the open and dense result for static regular surface. And based on theorem 2, we can derive this corollary, which tells us that the n-1 sphere in Rn is static regular. And this actually generalized the result from Anderson and Miao, where they prove S2, a sphere is static regular. Okay, so that's our result for static regular surfaces in Rn. And like proof for those theorems are very long and it takes lots of time to explain in detail. So here I will just show you the proof in the convex case. Okay, before I proceed, any question? Okay, so let's take a look at the convex case. So from now on, sigma is a convex surface in R3, and we consider the manifold M as the exterior region. Okay, the background metric is the flat metric. Okay, the first important observation is that for such sigma, actually we can always identify a Ricci flat deformation with diffeomorphism deformation, no matter what the boundary condition is. Okay, so the first aspect is written here. I suppose we have a metric G, induced metric on sigma, and it has positive Gauss curvature. Then we take arbitrary 2 tensor tau. We can construct this family starting from G sigma and then plus T times tau. So for T very small, we know this is the family of remaining metrics. And if T is small, the metric should also have positive Gauss curvature. Okay, then we know there is this embedding theorem, which tells us that we can find a family of embeddings which map the sigma into R3, maps GT to the induced metric in R3. Okay, so here is the picture. Sigma is the starting surface, and sigma T is just the image of sigma under this phi T. And this vector field X is the flow generated by this family of diffeomorphisms. Okay, then we can consider the Lie derivative of the flat metric with respect to X. And it's easy to observe that this induced tensor on the boundary sigma must equal to the deformation we start from here. Okay, so this means that given any 2 tensor on the boundary manifold sigma, which is convex, this tensor tau can be always realized as the Dirichlet data of a diffeomorphism deformation or of a flat deformation. And this is like a linearized version of the embedding theorem. Embedding theorem is telling us that if sigma is convex, I'm right here. If sigma is convex, has positive Gauss curvature, then we can the metric on sigma can be always realized as the Dirichlet data. This can be realized as the Dirichlet data of a flat metric on some surface. Yeah, and then the linearized version is that if sigma is convex and any tensor tau can be realized as the Dirichlet data of a flat deformation, of a diffeomorphism deformation. Okay, that's the first observation. Second observation is if we are given H, which is a Ricci flat deformation in the exterior region, and if H is with 0 Dirichlet data, then we can derive that actually H must be trivial, must be diffeomorphism deformation. So here is the reason. Now H is a Ricci flat deformation. We can trivially compare H with 0, with the 0 function. So H0 is a static vacuum deformation. And we choose an arbitrary kernel element, like choose arbitrary deformation generated by diffeomorphism. So this is also static vacuum deformation. So for those two, we plug those into the green type identity. Okay, so it's here. Into this green type identity, this will be 0, this will be 0. H has 0 Dirichlet data, so this term is 0. However, we don't know this term, so we keep it there. And we also compute the term here. Okay, so after simplification, we will get an equation like this. It tells that on the boundary, sorry. It tells that on the boundary, this boundary term of H is always perpendicular to the Dirichlet data of this diffeomorphism deformation. Okay, and from this first aspect, we know that the Dirichlet data of a diffeomorphism deformation can be arbitrary, can be prescribed arbitrary. So this term can be arbitrary. Therefore, we derive this H deformation must preserve the second fundamental form. Okay, so if H is Ricci flat, has 0 Dirichlet data, then it must have 0 Cauchy data. And we know that Ricci flat, 0 Cauchy will give us trivial deformation. Yeah. So therefore, if H is Ricci flat, with zero dilution data, then we must have H is equal to diffeomorphism deformation. Okay, so those two observations give us the following identification. A Ricci flat deformation is uniquely determined by its dilution data on the boundary, which is a symmetric two tensor on the boundary. And any symmetric two tensor actually can be realized as a diffeomorphism as the dilution data of a diffeomorphism deformation. Okay, therefore all of them can be, there is a one-to-one correspondence between those sets. Okay, so this is a very important observation for convex surface. Okay, and in particular, we can, given a symmetric two tensor tau on sigma, we can define this value, or this ring H prime tau. This is the mean curvature variation with respect to the Ricci flat deformation with dilution data tau. Okay, like in more detail, if we are given a symmetric two tensor tau, we can construct, say, flat deformation, xg flat, with dilution data equal to tau. And then we compute the mean curvature variation with respect to this flat deformation. Okay, this is denoted here. Okay, you might ask, we can, of course, construct another flat. The choice is not unique. There might exist another flat deformation with same dilution data, and we can compute the corresponding mean curvature variation. However, those two must equal. Okay, because we see here, the variation of second fundamental form is uniquely determined by its Cauchy data, by its dilution data. Okay, so for any tau, we can define this value uniquely. Okay, and this reminds us of, if you are familiar with the mean curvature comparison, this reminds us of the Shi-Tam theorem. Okay, so let's see. From Shi-Tam theorem, we know we can compare those two mean curvatures here. If omega is a compact manifold with boundary sigma, omega has positive non-negative scalar curvature, sigma is Gauss curvature positive, mean curvature positive, then we can compare those two mean curvature. This one is the mean curvature. This one is the mean curvature of sigma when it is embedded in the manifold omega G bar. Okay, and this is the mean curvature of sigma when it is embedded in the flat domain in R3 with induced metric G. That's right, G sigma. That's the induced metric. Sorry, that's the, but this has flat metric. So G sigma has induced metric. So this is the mean curvature of sigma when it is embedded in the flat metric. Okay, so we compare those two metric with, from Shi-Tam theorem, we know this quantity must be non-negative. Okay, and here, based on this previous observation here, we want to define a linearized version of this inequality. Okay, so we know that if we are given an arbitrary deformation K in the exterior region, we can consider the dilution data of K. Okay, that dilution data of K will be a symmetric two tensor on the boundary, and then use that two tensor, we can define this unique quantity, which is variational mean curvature with respect to the flat deformation caused by this K. Okay, and then we compare this with the classical mean curvature variation with respect to K. And you see those two are like a linearized version of those two. Okay, so we take subtraction and want to construct a similar quantity which must be non-negative. Okay, and then here we want to consider the difference between those two in the special case that this deformation K is equal to 2V times is a conformal deformation equals to 2V times the flat metric. V is some function on M. Okay, so we insert K as 2VG flat, we get those two quantity take difference. And actually, in addition, we want to multiply this with v, take integral. This quantity is a linearized version of this quantity. It's uniquely determined by the function v on M. And we show that actually fv is a C2 alpha function decays to 0 at infinity, and it's harmonic with respect to the flat metric, then this quantity must be non-negative. Okay, so that's our linearized version of Xi-Tan inequality. Okay, question so far? So here is a rough idea of why this inequality is true. Here, if we start with the harmonic function, we know that this conformal deformation 2Vg, because V is harmonic, so this deformation must be reach a scalar flat deformation. And we can construct a family of scalar flat metrics which deform G along this family. Okay, so here we construct a family G which always has scalar 0, which starts from the flat metric, and it's deforming along this scalar flat deformation 2Vg. Okay, that's the exterior region. And also construct a corresponding class of family of metrics in the interior region. Okay, we construct this family because eventually we want to apply this Xi-Tan inequality to the interior metric. Okay, once we have those family, we consider this functional. This functional is integral of scalar curvature plus this integral of the difference between mean curvatures plus mass term. Okay, so you see that when t is equal to 0, the metric is flat. So this term is 0. This term is 0. If this term actually achieves minimum at t equals to 0, and this term also it's always 0, so it has minimum at t equals to 0. So we construct this term so that it also achieves minimum at t equals to 0. Okay, so you see that when when metric is flat, ADM mass is of course 0. But if we deform the metric to a different one, ADM mass is not necessarily positive because now the exterior region is not complete. Okay, that's the reason we want to add this extra term, okay, to kind of cancel the deformation of the mass of the ADM mass in the family. Okay, so we define this term and we construct the family in a good way so that this functional achieves the minimum at t equals to 0. Okay, so we take second derivative, must be non-negative, and we compute second variation formula for this functional. We derive that this quantity HV, it must be non-negative. Okay, so that's the idea of proving this linearized version of Xi-Tan inequality. Okay, so once we have those two important tools, we can now come to prove the convex case at last. So now if HV is a static vacuum deformation in the exterior region, of course the boundary is convex and it preserves the Bartnik data on the boundary, then we first observe that H plus 2Vg is a Ricci flat deformation in the exterior region. This is simple, we just compute Ricci prime with respect to H plus 2Vg. This is exactly equal to Ricci prime H minus the Hessian, and that's 0. Okay, so H plus 2Vg is a Ricci flat deformation in the exterior region. So we know that it must be a trivial deformation. It must be a diffeomorphism deformation. Okay, so in particular, we know if we take linearization of H, this range H with respect to the Dirichlet data, it must equal to the mean curvature variation with respect to this deformation itself. Okay, so with this equality, we can now rewrite this quantity in terms of H. Okay, so it's like rewrite this quantity in the integral here in terms of H, because finally we want to derive A prime H. We want to derive quality on H. Okay, so we want to apply this inequality to the quantity here on H. Okay, and the idea is it's written here. So here sigma is the starting convex surface. We know HV is a static vacuum deformation in the exterior region. And then we deform sigma for a short time along the unit normal vector. Okay, so we get a sequence of surfaces. Okay, and on those sequence of surfaces, we consider a smooth family of harmonic functions Vt in the exterior region of those surfaces sigma t. And we know because Vt is harmonic, therefore this functional should always be non-negative. Okay, and in particular, we can choose this family of Vt to be equal to V in the exterior region here. Okay, because we already have a V defined there, so we just restrict the value of V on those exterior regions. Okay, so we know this functional must be non-negative, and in particular, it equals to 0 when t equals to 0. Okay, it's just because when t equals to 0, what we have? This difference is equal to this term. However, H has vanishing Bartnik data, so this is 0. This H tangential part is also 0. So when t is 0, that term is 0. Therefore, this functional achieves minimum at t equals to 0. So we take derivative at t equals to 0, we should also get 0. And that's the idea we have here. We replace those V term by H term, take derivative at 0. And in the calculation here, we want to apply Riccati equation and also apply the green type identity again. And finally derive that this actually tells us that A prime H is equal to 0. Okay, so this tells us that in the convex case, if H is preserving the Bartnik data, it must also preserve the second fundamental form. That's the definition for static regular. Okay, so that's finished the proof of the convex case. Okay, yeah, that's the end of my talk. Thank you for your attention.
Thank you, Zhongshan, for a very, very interesting talk. Just thank her for the talk. And please, if you have any question, unmute yourself and feel free to ask your question.
Hi, do you have examples of, do you know of any examples of not regular surfaces?
There might be possible counterexample for non-existence if the surface is not embedded. Like it's provided in the paper of Anderson and Harigi. Like if a surface look like this. Sorry.
Okay, but no ideas for what an embedded example might look like?
Yeah, we don't know. Yeah.